Nenomatica, where mathematics meets YouTube excellence. Example: we will solve the radical equation by the substitution method. 2x squared plus 3x minus 5 times the square root of 2x squared plus 3x plus 9 plus 3 equals 0. Step 1. Substitute the radical with a new variable to simplify the structure. We'll define t as the square root of 2x squared plus 3x plus 9. To prepare for substitution, add and subtract 9 to bundle the polynomial inside one group. Step 2. Replace the group terms using t. Since t squared equals 2x squared plus 3x plus 9, the equation becomes t squared minus 5t minus 6 equals 0. The negative 6 is highlighted because it comes from negative 9 plus 3. Step 3. Solve the quadratic in t using the quadratic formula. T equals 5 plus or minus the square root of 25 minus 4 times 1 times negative 6 all over 2. That simplifies to t equals negative 1 or t equals 6. Step 4. Check the domain. Because t equals a square root, t must be greater than or equal to 0. Therefore, t equals negative 1 is not acceptable, and we keep t equals 6. Step 5. Back substitute t equals 6. The equation becomes the square root of 2x squared plus 3x plus 9 equals 6. Square both sides and rearrange to get 2x squared plus 3x minus 27 equals 0. The final answer is x equals 3 or x equals negative 9 over 2. Display the word example. Then, show the problem in bold orange math. Step 1. Use substitution. Show the rule box for the substitution method. Add the step title. Replace the fourth root with t, and note that the square root becomes t squared. So the equation becomes t squared plus t equals 6. Step 2. Rearrange into standard quadratic form. Show the rule box for the quadratic form. Add the step title. Move all terms to the left to get t squared plus t minus 6 equals 0. Step 3. Solve the quadratic using the quadratic formula. Show the quadratic formula rule box. Add the step title. Compute the discriminant. B squared minus 4ac equals 25. Find the two roots, t equals 2 and t equals negative 3. Step 4. Apply the domain restriction for radicals. Since t equals the fourth root of x cubed plus 8, t must be non-negative. Show the rule box expressing t is greater than or equal to 0. Add the step title. Therefore, we keep t equals 2 and reject t equals negative 3. Step 5. Back substitute and solve for x. Show the back substitution rule box. Add the step title. Set the fourth root equal to 2, then raise both sides to the fourth power. We get x cubed plus 8 equals 16. Then x cubed equals 8. Finally, x equals 2. Quick challenge. Can you verify by direct substitution that x equals 2 satisfies the original equation? Substitute x equals 2 and show both radicals sum to 6. Therefore, the solution to the equation is x equals 2. Example: we will solve the radical equation exactly as shown in the source steps. First, display the problem clearly in bold orange. Step 1. Determine the domain of the expression under the even root. We require x to satisfy x to the fifth plus 32 greater than or equal to 0. That gives x greater than or equal to negative 2. Step 2. Use substitution to simplify the radicals. Let t equal the sixth root of x to the fifth plus 32. Then t is greater than or equal to 0. Notice the cube root becomes t squared, so the equation becomes t squared plus t equals 2. Step 3. Form and solve the quadratic equation. Move all terms to one side to get t squared plus t minus 2 equals 0. Factor to obtain t minus 1 times t plus 2 equals 0. So t equals 1 or t equals negative 2. Step 4. Apply the domain restriction t greater than or equal to 0. Therefore, only t equals 1 is acceptable. Step 5. Back substitute t equals 1. The sixth root of x to the fifth plus 32 equals 1. Raise both sides to the sixth power to get x to the fifth plus 32 equals 1. So x to the fifth equals negative 31, and x equals the fifth root of negative 31, which is negative the fifth root of 31. Step 6. Verify the domain and confirm the solution. Since the fifth root of 31 is about 1.99, our x is approximately negative 1.99, which is greater than or equal to negative 2. Therefore, it satisfies the domain. Finally, check in the original equation x to the fifth plus 32 equals 1. So both the cube root and the sixth root equal 1, and the sum is 2. The solution is valid. Final result. The equation has the single real solution, x equals negative the fifth root of 31. Example, we will solve the radical equation and determine n in natural numbers. Given the equation, the nth root of 17 times square root of 5 plus 38, plus the nth root of 17 times square root of 5 minus 38, equals the square root of 20. Step 1. Define a substitution. We let x be the nth root of 17 times square root of 5 plus 38. This will make the equation algebraic in terms of x. Step 2. Relate the second radical to x. Notice that the product of the two radicands is 1, because 17 root 5 plus 38 times 17 root 5 minus 38 equals the square of 17 root 5 minus the square of 38, which is 1. Therefore, the nth roots multiply to 1. So the second term equals 1 over x. Step 3. Substitute into the original equation. We obtain x plus 1 over x equals the square root of 20. Step 4. Multiply both sides by x and rearrange to a quadratic in x. Step 5. Solve the quadratic with the quadratic formula. Here, a equals 1, b equals negative square root of 20, and c equals 1. The discriminant is 16. Therefore, x equals the square root of 20 plus or minus 4, all over 2, which simplifies to square root of 5 plus or minus 2. Step 6. Determine n. Let x equal square root of 5 plus 2, which is the nth root of 17 root 5 plus 38. Raise both sides to the power n. We want the right side to equal 17 root 5 plus 38. Testing n equals 3, and expanding shows that square root of 5 plus 2, all cubed, equals 17 root 5 plus 38. Thus n equals 3. Step 7. Observe the reciprocal relation. Because the product of the two nth roots is 1, the second term equals 1 over x. Indeed, square root of 5 minus 2 equals 1, 1 divided by square root of 5 plus 2. That matches the other radical expression. Final result. The equation holds for n equals 3, and the substitution yields x equals square root of 5 plus or minus 2. Great work! Welcome! In this example, we'll solve a nested radical equation by following a clean substitution algorithm. After the example label, we'll display the problem in bold orange math, then proceed step by step. Step 1. We'll name the entire nested radical by a single letter. The rule here is substitution for a repeating nested form. Let the whole radical equal x. We'll keep it visible as our starting equation. Step 2. We square both sides to remove the outer square root. The rule is the square of a square root equals the inside. After squaring, the left becomes x plus 2 times a very similar nested radical, and the right becomes x squared. Step 3. That inner nested radical is the same repeating structure we named earlier, so we substitute it by x again. This gives x squared equals x plus 2x, which simplifies to x squared equals 3x. Step 4. Move all terms to one side, then factor. We'll use standard quadratic rearrangement and factoring. First, x squared minus 3x equals 0. Then factor x times x minus 3 equals 0. Step 5. Apply the zero product property. If a product is 0, at least one factor is 0. So x equals 0, or x minus 3 equals 0, which gives x equals 3. Both are non-negative, so they satisfy the definition of the radical. Example. In this problem, we will solve the exponential radical equation exactly as shown in the provided algorithm. Here is the equation read as the cube root of 2 plus square root 3 raised to the x plus the cube root of 2 minus square root 3 raised to the x equals 2. Step 1. Express the equation using a helpful identity and substitution. Note that the cube root of 2 minus square root 3 equals the reciprocal of the cube root of 2 plus square root 3, because their product equals 1. We'll then rewrite the equation in terms of a single base. Now define y to be the cube root of 2 plus square root 3 raised to the x. With this substitution, the equation becomes y plus 1 over y equals 2. Quick challenge: can you predict our next algebraic move to eliminate the denominator? Think about what to multiply both sides by. Step 2. Form a quadratic in y. Multiply both sides by y. That gives y squared plus 1 equals 2y. Move everything to one side to get a standard quadratic. Y squared minus 2, y plus 1 equals 0. Step 3. Recognize a perfect square. The expression y squared minus 2, y plus 1 is the square of y minus 1. So we write left parenthesis, y minus 1 right parenthesis squared equals 0. Therefore, y equals 1. Step 4. Back substitute to find x. Recall that y equals the cube root of 2 plus square root 3 to the power x. If a positive base not equal to 1 raised to x equals 1, then x must be 0. We set the expression equal to 1 and conclude x equals 0. Example: we will solve the equation x over the quantity 2 plus x over square root of x plus 1 equals 1. We will simplify the complex fraction first, then isolate the square root, square both sides, and finally check for extraneous solutions. Step 1. Simplify the denominator 2 plus x over square root of x plus 1 plus 1. We rationalize the inner denominator with its conjugate, square root of x plus 1 minus 1. After multiplying top and bottom by the conjugate, the difference of squares gives x in the small denominator. This simplifies to 1 plus square root of x plus 1. Step 2. Substitute the simplified denominator back into the original equation. The equation becomes x divided by 1 plus square root of x plus 1 equals 1. Step 3. Cross-multiply to isolate the radical term. We get x equals 1 plus square root of x plus 1. Move 1 to the left, x minus 1 equals square root of x plus 1. Step 4. Square both sides to remove the square root. Then expand and simplify. Step 5. Check each candidate in the original equation to avoid extraneous solutions created by squaring. 4x equals 0. The left side becomes 0 over 2, which is 0, not 1. So x equals 0 is extraneous. 4x equals 3. The denominator 2 plus 3 over square root of 4 plus 1 equals 3. So the left side is 1. Therefore, the only solution is x equals 3. Summary: we simplified the complex fraction. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.